In the last class, essentially, we discussed the mean of the new random variable g of x, where g is the given function and x is the given variable, given random variable. So we discuss what is the expectation of g of x, and again here, whenever the gx function takes the negative values, we need to check the absolute convergence here for the existence of the expectation. And expectation cannot be infinite, it should be a finite, some finite number, should be some finite number, right? So we discussed the mean of the random variable gx, and this is the continuous version of that. Continuous version of that, and we have seen some examples. Also, we discussed the mixed random variable case, and then we discuss the nth moments. So nth moment of a given random variable is defined using the function gx equals to x power n, right? Gx equals to x power n, and it is defined in this way that in the discrete case it is summation x power n fx, where fx is a probability mass function of random variable capital X, and in the continuous case it is a integral x power n fx dx. And then we define central moments by the function gx equals to x minus mu power n, where mu is the mean of random variable x. So the central moment is defined corresponding to the number n, So whatever n is given, correspondingly we can define the nth central moment. And second central moment is variance. Second central moment is variance. So variance is what? That is expectation of x minus mu square, right? X minus mu power 2. So in discrete case we have defined similarly. For the continuous case it is just replacing summation by the integration. And then we have defined the standard deviation, which is the square root of the variance. So we have not discussed why variance should be non-negative. We have not discussed that, but that we'll discuss in the today class. We'll show that variance is always a non-negative number. We'll prove it using the linearity property of the integral. And then we have seen some examples. What is the variance in the case of geometric random variable? Okay, so in the last class I have given one example exercise, that if you have a uniform continuous random variable over the closed interval AB, then what is the variance? So that I will be using in today class. So let us first verify that. So what is our random variable? That is uniform distribution over closed interval AB. We already know that its mean is 1 upon, what is the mean? A plus b by 2, right? So a plus b by 2. Okay, so what is we want to find the variance. We have variance formula. So variance of x is essentially, this is a continuous random variable, so that is integral minus infinity to infinity x minus mu square fx of x dx. And we know that if you have a uniform random variable, fx is defined as 1 upon b minus a over the interval, and otherwise it is 0. So let us substitute all these values here. So since our probability mass function or the density function is defined only for the interval a to b, right? Otherwise it is 0. So that means it is essentially the integral over the interval a to b, right? It is integration a to b x minus mu square, and mu is the average a plus b by 2, a plus b by 2, that is our mean, and its square times fx over this interval is 1 upon b minus a, 1 upon b minus a dx. So we need to find this integral, and we can take first the constant out, that is b minus a, and the integral of x minus some fixed number square. So that is same as either you can change the variable, we can change the variable, or we can directly integrate, right? So integration is x square is x cube by 3, right? So here the integration is x minus a plus b by 2 cube by 3. So 3 we can take together with the denominator b minus a, and the integration is x minus a plus b by 2 power 3. Limit is x equals to a to b, x equals to a to b. So now we will substitute it. The upper limit is x equals to b. So when we substitute x equals to b and subtract a plus b by 2, so that means b is 2b by 2 minus a minus b. So that is 2b minus b is b minus a, right? So that is b minus a by 2 right. So b minus a by 2 power 3, and when we substitute the lower limit, so that means we have the minus sign, that will be a minus b by 2 cube. So now the common term we can take outside, that is b minus a power 3, right? So if you take that common term outside, that is essentially b minus a power 3. The remaining will be 1 by 2 power 3, that is 1 by 8, minus here we have a minus b cube, but we have taken b minus a cube outside, that means there will be minus sign. So that will be plus 1 by 8, right? So now when we add these, b minus a, 1 b minus a we will cancel out. So in the numerator it will be b minus a square divided by 3 into 4, right? 3 into 4. So that is the final answer is b minus a square by 12. B minus a square by 12. So what did we found? We found the variance of the uniform random variable over the closed interval AB. And what is the standard deviation? So positive, right? So b minus a anyway is positive because what interval is a to b. So b minus a by square root 12 is the standard deviation in this case. Okay. So next is some properties of expectation. So we want to show that the variance is a non-negative number, so that we need some properties of expectation, and we know that expectation is defined in terms of integration or summation, right? So something which is defined in terms of integral or summation. So we know that integration is a linear operator, right? Integration of 2x plus 3 is essentially 2 times integration of x plus 3, right? So that is a linear operator. So using the linearity of integration, we'll show that expectation is linear. Expectation is linear. So what is the statement? Statement is suppose let x be a random variable, and we have expectation of two functions which are finite. So expectation of g1x and expectation of g2x exist. So g1 and g2 are two functions such that their expectation exists. Exist means it is a finite number. It is not infinity or minus infinity. It is a finite number. Okay, so then what we want to prove? We want to prove that the first part is it is linear. That means expectation of ax plus a g1x plus b, that is since it is linear, we want to show that it is expectation of g1x, this is a random variable, plus b, right? So it be preserves the linearity, like differentiation and integration. It is a linear operator. And second thing we want to prove is that if one function dominates the other function pointwise, then the expectation of g1 also should be the greater than equals to expectation of g2, right? So that we want to show. So everything which we will show is will show in terms of the integration. Everything is in terms of integration. So the first part, when we show, what is that? That is expectation of a g1x plus b. So what is that? So here we are considering this variable a plus a g1 x plus b as some function of x, right? It is a function of x like gx. So let us call it hx kind of thing. And then we have some function of random variable x. Then we know that what is its expectation. So if the function is g, we know that the expectation is integral gx times fx of x, right? So here it will be hx times fx integral, where hx is a g1x plus b, right? So by the very definition of the expectation of function of random variable, this equals to integral, because we are considering the continuous case. The discrete case is similar. So that is g1x plus b times the mass function or the density function. So when we integrate, now we can see that this is integral in terms of x as a linear function. So we can separate the terms. So when we separate the terms, what we get, that is equals to a times integral g1x fx of x dx plus b, right? So why it is b? Total integral is 1, right? So area over all minus infinity to infinity fx is 1. So that is exactly we are using here. So that is right, that we are using the integral fx is 1, and we'll be using this again and again in this lecture, at least one times more. So just remember that. So now what is this? That is a of the expectation of g1x plus b, right? So we proved that the expectation is essentially the linear operator, but the variance is not. Right? We'll see later. The variance is not a linear operator because expectation is defined in terms of x minus mu. That is linear, but x minus mu square is not linear. Right? So that is the reason why it is not linear. Second part we want to prove, that is If g1 greater than equals to g2, we want to show that expectation g1 greater than equals to expectation g2, and then we know that what is the expectation of g1, that is g1 fx integral, right? So if you can show that g1 fx is greater than equals to g2 fx, that is enough, right? And that follows because fx is non-negative, right? Probability function is non-negative. Fx is always non-negative. So what is given? Given is that, suppose that g1x is greater than equals to g2x for every x, then since fx is non-negative, it will not change the inequality if you multiply by fx at each point. So therefore fxx is greater than equals to g2x fxx for every x, right? So every point wise we are multiplying, and now we will integrate from minus infinity to infinity. So therefore the integral g1x fxx is greater than equals to integral g2x fxx. Right. So in this step we are assuming that expectation is a finite number, right? So it exists. So that we have used here, and then what we'll get is expectation of g1x is dominates expectation of g2x. So this result we are going to use to prove that variance is a non-negative number. Variance is a non-negative number, right? So what is the variance definition? We define it as the integral of x minus mu square, right? And we know that x minus mu square is always non-negative, right? So that we are going to use as a proof. So what we are going to discuss is a remark. So variance of the random variable x, that is defined as integral minus infinity to infinity x minus mu square fxx dx, and since x minus mu square, mu is a fixed number, so this is always non-negative for each x. It is always non-negative for each x. So now you multiply by fx and integrate. So we get integral x minus mu square fx, and 0 means it is a zero constant function 0. So that its integral is also 0. So that means it is greater than equals to 0. So what we use is using part 2, part B of the last result, previous result. Okay, so what did we prove? We proved that variance of x is non-negative. So since it is a non-negative number, we can take its square root. That is the standard deviation, right? So standard deviation is a positive square root of this, and so now using this information we can find alternate formula for expectation for variance. Alternate formula for the variance. We can find alternate formula for variance. So what we are going to use is we are going to use the original formula, that is variance of x, that is defined as expectation of x minus mu square, expectation of x minus mu square, and then x minus mu square, we know that that is x square plus mu square, sorry, yeah, x square plus mu square minus 2 mu x, right? So now we will use the expectation is a linear operator. So expectation is a linear operator, part 1 of the last result. So that we apply, we get expectation of x square minus 2 mu times expectation of x plus mu square times expectation of 1. What is expectation of 1? That is 1. Again, the total area is 1. Right? Integration fx is 1. Again, we are using. So we get this term. Now we know that expectation of x is a mean, that is mu, right? So that means that term will become 2 mu square. So expectation of x square minus 2 mu square plus mu square. So that is we get expectation of x square minus mu square. And what is mu? Mu is expectation of x. We can substitute it back. So what we get is expectation of x square minus expectation of x the whole square. So this is another formula of variance. Another formula of variance in terms of moments. In terms of the moments. So expectation of x is the first moment, that is mean, and expectation of x square is the second moment, right? So using that we can find this. Using that we can find this. So now we know that variance is non-negative number. Variance is a non-negative number. So from that what we get? This is non-negative. So this term is smaller than this term. Right? This term is smaller than this. So let us note down that. So remark. So since we know that variance of x is non-negative, therefore ex square is greater than equals to expectation of x the whole square, So if it is a continuous random variable, what does this means? If x is continuous, we get so this is just in terms of integral, that is minus infinity to infinity x square fx of x dx, that is greater than equals to integral minus infinity to infinity x fx dx its square. So what does this means? This means whenever this integral is convergent, this is convergent, right? This integral is convergent because this is always non-negative, so it cannot be minus infinity, right? This is a non-negative number. So this is always so basically we are using the dominated convergence or squeezing kind of idea, right? So you can relate with the series also. So what is actually happening here? Actually happening that integration of x square, if we call this is the weight of the integration, fx is the weight of the integration, then integration of x square is finite, then integral of x is finite, right? Integration of x square is finite, then integral of x is finite. So this is a special case of Jensen's inequality. So let us consider the discrete case. If x is a discrete case, So then we need to replace the integration by summation, which is greater than or equals to summation x fx of x, x fx of x, the whole square. So now if you have the random variable, which is a uniform random variable of tossing of a coin. So what is the random variable? Which two values it takes? 0 and 1, right? So 0 and 1 are not important in this random variable, right? It is just assigning two values to two outcomes, right? So we can define any two real number instead of 0 and 1. So let us call the numbers are x1 and x2 with the same probability half. So then what this quantity will become? That is x1 square probability, that is half, plus x2 square probability half. So that is average of these two number, right? So what are x1 and x2? That is in the range of the random variable, right? x1 and x2 are any two real number. It may be 0, 1 or any two real number. And on the other side, what we get? x1, x2 by 2. So this is arithmetic mean of two numbers. Correct. So that I have not written. So what is x1 plus x2 by 2? That is arithmetic mean of the x1 and x2. And on the other side, we are getting arithmetic mean of the x1 square and x2 square. So there must be square here, right? There must be square here. So this type of inequality, this is essentially the Jensen's inequality for numbers. And numbers x1, x2, you can extend it for the n numbers also, right? Uniform discrete random variable with n outcomes. Okay, so this is a special version of Jensen's inequality. Jensen's inequality has many versions. Okay, so this is what essentially we are getting in terms of numbers, but what we have received as a random variable is this information. So this is first remark. The second remark is that integrability. So let us write down that also. So whenever the integral x square fx x dx is finite, we have this integral is also finite. This integral is also finite. Okay, so this is regarding the second form of the variance, second equation of variance. We'll come back on this. So now we have found the expectation of ax plus b, that is a times expectation of x plus b, because expectation is a linear operator. Now what is ax plus b? That is the first case of the when we discuss the shortcut formula, right? So we have discussed different types of examples of the random variable which is coming from x. So linear, quadratic, all these things we were discussing. So ax plus b we have discussed expectation. Let us find the variance of ax plus b. Variance of ax plus b. So this is a small proposition. So whenever variance of x is a finite number, we have variance of ax plus b is a square times variance of x. A square times variance of x. So these are the essentially the properties of variance. So here we will use the second formula. So if you have a variance of ax plus b is considered as some variable y. random variable y. So that means what is the variance? Variance of x is expectation of x square minus expectation of x the whole square, right? So we need to substitute this ax plus b there instead of x. So that is expectation of ax plus b square, right, minus expectation of ax plus b the whole square. So now in the first term we will first square and then apply the operator e, which is linear, right? And in the second term we need to first apply e on ax plus b. We will use the linearity and then we'll square it. So let us simplify this. So that is expectation of ax square plus 2abx plus b square, right, minus expectation a times expectation of x plus b the whole square, right? So correct. So in first term there must be a square, right? So that is a square x square. Okay. So now we will apply that expectation is a linear operator. So a square will come out. So that is a square expectation of x square plus 2ab expectation of x plus b square times expectation of 1, that is 1, minus now we have these two as a numbers, as a real numbers. So that is a plus b square formula. So that is a square expectation of x square plus 2ab expectation of x plus b square and so is it correct or okay, so that is right. So now what will be cancelling? 2ab expectation of x will cancel, b square will cancel, the remaining we can take a square common, right? So that will be a square times expectation of x square minus expectation of x the whole square. And what is this quantity? That is variance of the first random variable x. So you can see that variance is not a linear operator because variance of ax plus b is not a times variance plus b, it is a square times variance, right? So these things we can use in some example. So consider a random variable that is y equals to minus 2x plus 3 if expectation of the random variable y is 1, expectation of random variable y square is 9, then find the mean and variance of the random variable x. So this is a linear equation, so you can find it. The expectation is a linear operator. We know expectation of y, we can find expectation of x. So what is the answer? One is the expectation, and what is the so variance is 1/4. So how did you find the variance? We have the random variable y is minus 2x times 3. So what is the variance of y and variance of x relation? A square times, right? So that is a is minus 2, so a square is 4, right? So 4 times variance of x. So first you find what is variance of y, substitute, and then you will get variance of x. Okay, let me check. So expectation of x is 1, right? Hint or answer. Expectation of x is 1. What is variance of y? That is 8. And what is variance of x? That is 2, right? Right. So that's the result we are using here, and you can find this. Okay. Okay. So today we want to discuss the moment generating function. So we know that if we are given the random variable x, we can create a new random variable, the y in terms of x. Then we know its expectation. What is the formula of its expectation, that we already know. So there are some examples in the tutorial also. You have seen that we have considered the random variable e power x, right? E power x. So e power x is related to the function ex. The same way here we are going to consider the moment generating function, that is the random variable e power tx, its expectation. So let x be a random variable, and consider new random variable, that is exponential of t times x, where t is a real number, that is also called the parameter. And what is the moment generating function? The moment generating function is defined by mxt. So m corresponding to the given random variable capital X at t, that is defined as expectation of e power tx, right? So by definition it will be equals to what? Okay. So what will be the discrete case? Summation gx fx. So what is gx here? E power tx. That is the random. That is the function, right? Gx function is e power tx. So it is g of x, where g of x is a random variable, new random variable, where that is e power tx. So we have gx times fx, that means e power tx times fxx. So this is our discrete case. This is our discrete random variable case. And if we have the continuous case, उसमें क्या आएगा? integral, same e power tx, same formula. So you can see that here we have the function fx which we are integrating along with the function which is a function of two variables t and x, right? So it is like a Laplace transform, right? So if you remember the Laplace transform, Laplace integral, right? So we have used Laplace transform. When did we use? To solve the differential equations, if you remember, in the mathematics 2 course at the end, right? So Laplace transform we can use to solve the differential equation, that is the integral transform. So that also has the function which we are integrating along with the kernel, which is a two variable function, Okay, so those things anyway we are not using, but just mentioning that this is a integral transform, and we are going to use this formula. So let us start with the simple example of the uniform random variable. Over 0 to 1. So what we want to find is we want to find the moment generating function of this random variable. So this is also very simple. What is the fx here? That is 1 if x is in the closed interval 0 to 1, and otherwise it is 0. So this is the density function, and this is a continuous random variable. So we'll use the second formula, this formula of the probability mass of the generating function. So if you substitute it, it is what will we get? Mx of t is integral minus infinity to infinity e power tx fxx. This is the formula. Now it is non-zero, fx is non-zero over this interval, and its value is 1. So if you use both these things, we'll get the integral 0 to 1. This is 1, right? Value of the function is 1. So that is e power tx dx. And when we integrate with respect to x, t variable is constant, right? So what is the integration? Integration is e power tx by t, right? And integration is from 0 to 1. Okay. So when we substitute these, the upper limit will be e power t. 1 upon t is common, we can take outside. So when x equals to 1, it is e power t. When x equals to 0, it is 1, right? So e power t minus 1. E power t minus 1. Right? So we have this moment generating function of the discrete uniform random variable, and that turns out to be the function 1 by t into e power t minus 1, e power t minus 1, and e power t has the power series expansion, right? So power series expansion we have, that means not every function has a power series expansion, but the functions which are infinitely many differentiable, which are differentiable infinitely many times, that is the power series expansion. So here the function is e power t. 1 upon t is not infinitely many differentiable, times differentiable, but 1 by t times e power t is infinitely many times differentiable. It has a power series expansion, right? So whenever we have the moment generating function which has the power series expansion, then we can get back the moments using this function, right? We can get back the moments using this function. So that is our next result. So assumption, we know that it is if we have the moment generating function mx of t. So this is a function of the variable t. This is a function of the variable t. So if it has power series expansion, means it has a power series in powers of t, right? In powers of t. So that is summation k running from 0 to infinity t power k divided by k factorial times the coefficients. Like what is the coefficient? Coefficient is nth derivative at 0. We are expanding at 0, right? So suppose that the moment generating function is analytic, that means has power series expansion. In that case, then the coefficients of the power series gives us moments by the following formula. So this formula we are going to prove, that is moment generating function equals to summation k equals to 0 to infinity t power k divided by k factorial times the kth moment. So we are going to prove directly using the expectation definition of the moment generating function. So by the definition itself, we will show this. So what is the moment generating function? That is expectation of the random variable e power tx, e power tx. So now e power tx is the function gx, is the function gx, and that function is e power tx, so it has a power series expansion, right? In terms of the power tx, in terms of the power tx. So therefore, this term we can write as a so how we'll write that? That is expectation of summation k running from 0 to infinity, k running from 0 to infinity t power k x power k divided by k factorial, and then we know that expectation is a linear operator, right? So when we apply the expectation on summation, summation will come outside. It is a linear operator, and then this is a number t power k by k factorial. So number will also come outside because it is a linear operator. So that will be expectation of x power k. Everything else will come outside. So this term is our kth moment, expectation of x power k, that is our kth moment of the given random variable x, right? Okay. So what we will do now, we are given the random variable, we will first find what is the moment generating function, right? And then whatever moment generating function is there, it has a power series expansion. That power series we will compare with this power series. So we'll get the corresponding term, right? Corresponding term. Okay, so example is the same example. We'll take the last example where we have found the moment generating function. So let x be the uniform random variable over the interval 0 to 1, and in this case we have found that our moment generating function is essentially, what is the moment generating function? 1 divided by t e power t minus 1, right? So now this has a power series expansion that we will substitute here. So that is 1 by t times 1 plus t square by 2 factorial plus t power 3 by 3 factorial minus 1, right? So 1 will cancel with this minus 1, and then we'll divide each term by t. So that means the first term will be 1, second term will be t by 2 factorial, plus third term will be t square by 3 factorial, and so on. So these terms we are going to compare with the power series. Summation an x power n by n factorial. Here t power n by t power k by k factorial, right? So that is, if you compare, what is the power series? That is a0 plus a1 times t plus a2 times t square by 2 factorial plus a3 times t power 3 by 3 factorial, and so on, and so on. So now if you compare this term by term, what is a0? A0 is 1. So that is expectation of e power k. K is 0, right? Because a0, k is 0. So that is x power 0. That is exactly expectation of 1, which we already know. It is 1 always, right? What is a1? A1 is, you compare this term and this term. So that is 1 by 2. That is expectation of the random variable x, right? What is x? X is the uniform random variable over the closed interval 0, 1. And we know that UAB has the mean as a plus b by 2. So that means U01 has the mean 0 plus 1 by 2, that is half, right? So we have verified that we are getting the correct answer here, that expectation in this case is half, which is coming from the moment generating function as same as what we are getting directly. Now what is A2? That is 1 by 3, right? So 1 by 3 is expectation of x square. So for the uniform random variable, we have not computed expectation of x square, but we have found the variance, and we know that variance has equation in terms of the expectation of x square, right? So what is the variance in this case? One by 12, right? Because we found that that is b minus a square by 12. Let us go back to that example. That is the first example, right? Okay. So if our random variable is u01, we know that the variance is 1 by 12, 1 by 12. So what is expectation of x square? That is variance plus mean square. So variance is 1 by 12 plus mean is half square. So that is 1 by 12 plus 1 by 4. तो कितना आएगा ये? 1 by 3, right? So that is 1 by 3. So you see that also equals to this expectation, whatever we are getting here. right? But expectation of x3 we cannot find until we find the other quantities, right? Expectation of x minus mu power 3, and then you find you get expectation of x power 3. But if you know moment generating function, we can directly find the third moment, right? We can directly find the third moment. So moments are important because it has a relation with mean, variance, and the other statistical terms. It is related. Okay, so let me give you one exercise example which you can do now. So that is we have the random variable exponential lambda. So what is its density function? That is lambda e power lambda x. X is non-negative. We have 0. So we want to find expectation of x square and variance of x. Variance of x. So we have done this example to find the mean. So what is the mean? The mean of the exponential random variable is 1 by lambda. Right? Exponential lambda random variable is 1 by lambda. So we know mean now. Using so first you find exponential the expectation of the random variable x square, and then you compute what is the variance. So what is expectation of x square? That is just integral x square fx, right? That is just integral x square fx. So fx is given, that is lambda e power minus lambda x, and you need to integrate from 0 to infinity. So if you recall, how did we found the mean of this random variable? So we use the integration by parts formula, right? Integration by parts formula. So here also we are going to use the same thing. We have the function x square times e power minus lambda x, that we need to use the integration by parts. Moment generating, yeah, you can do that. So did you find what is moment generating function? That is yeah, but you find what is this value, t minus x. Okay, so t is a real number, yeah, so it depends on t. So you define using t less than lambda, t greater than lambda. So you get like a step function kind of thing.
For t less than lambda, it will be 1 upon t minus x.
Yeah, so in that case you will get the function. Once you get the function, you can use that.
So,
But in that case, how you will get the things? Yeah.
Yes, so whenever t will be greater than lambda, that time it will
Yeah. So in that case, what you will define 0 to infinity. So that means x minus lambda. Lambda is fixed. T is also fixed.
yes.
T is fixed. Lambda is fixed. So t minus lambda is fixed. X is positive, and x goes to infinity. Yeah, but you have to find for each t lambda is fixed for, you will get two cases. What you are saying is you will get infinity.
Yes, so whenever t will be greater than lambda,
T is greater than lambda.
that case,
T is greater than lambda. So if t t is greater than lambda, what to do in this case? So t is greater than lambda, that means t minus lambda is positive.
minus
Yeah, so in this case, we are not exactly getting the moment generated. I will see this. Yeah. So you put exponential of e power ext, right? X lambda e power xt power lambda x minus lambda x, right? Yeah, yeah, that is correct. 0 to infinity. Infinity, if you put, you can't put directly. In that case, what to do? Can you expand first and then integrate?
means I will expand this series.
Yeah, you see, I will see also. X square is 4. 4, it will come in terms of lambda. Correct, correct. Okay, so let me do this example. Many of you have done already. So what is expectation of the random variable x square? That is 0 to infinity x square e power minus lambda x dx. So we are going to integrate this function, and we know the integration by parts formula. So we can use the generalized version of that, that is x square times e power minus lambda x by minus lambda minus 2x times minus lambda x square, and the last term is plus 2 times e power minus lambda x by minus lambda power 3, and the limit is from x equals to 0 to infinity, right? So when we substitute uh, the upper limit, e power minus lambda x is 0, because lambda is a positive number. Lambda is a positive number. So, and when we substitute the lower limit, x equals to 0, these two terms are 0, 2x and x square. Only the last term will remain at x equals to 0, and with the lower limit, so with the minus sign. So what is the final answer? That is 2 by lambda square, right? And then we have the variance. So variance, we know that that is formula expectation of x square minus expectation of x the whole square. So that is 2 by lambda square minus 1 by lambda square. That is, finally it is 1 by lambda square. 1 by lambda square. Okay, so I think this is enough for the today class. So let me stop here.